Hey everyone, and welcome. Today we're going to unlock one of the most powerful tools in calculus for describing movement, vector functions. If you've ever wanted to know how we can mathematically map out a path in 3D space, well, you are in exactly the right place.
Really think about it for a second. How do you program the flight path for a drone? Or how do you tell a video game character exactly how to navigate a complex 3D world? Well, the answer is vector functions. It's the math we're about to dig into. This isn't just about numbers on a page. This is literally the language of motion.
Okay, let's get right to it. So what is a vector function? Well, at its heart, it's just a rule. It's a function where you plug in one single number, t, and you can just think of t as standing for time. For any moment in time t that you put in, the function spits out a vector, basically an arrow pointing from the center of your graph to a specific point in space. So as t moves forward, second by second, the tip of that vector draws a path. It traces out a curve. And that single idea, that's the engine that powers everything we're going to do today.
So here's our quest map for this explainer. We're going to start with the absolute basics. Then we'll gear up with our mathematical toolkit. And after that, we're going to conquer 3 different levels of challenges. Figuring out where a path can even exist, drawing a perfectly straight line, and finally, identifying a classic spiral curve. And at the end, we'll see what's next on the horizon.
So, let's start right at the beginning, with the building blocks. If you can really get these core ideas down, the examples we're about to do will make so much more sense.
There are a few common shapes that just pop up over and over again. So, if your x, y, and z components are all just simple linear functions of t, you're going to get a straight line. Easy enough. Now, if you spot sine and cosine showing up in 2 of the components, you should immediately be thinking circle or ellipse. And what if you have that circle motion happening, but the third component is also moving in a straight line? Well, that's a helix. Just picture a spiral staircase.
All right, every quest needs the right gear, so think of this section as us gearing up, grabbing the essential formulas we're going to need to solve the upcoming challenges.
Okay, here are our 2 essential tools for today. First, you've got the general form of a vector function, which we've already seen. But the second one, this is the really clever one. It's the formula for a line segment that goes from some point P to another point Q. Just think of it like a blend. When t is 0, the formula gives you 100% of point P. When t hits 1, it gives you 100% of point Q. And for any t in between, say 0.5, you get a perfect mix of the 2, putting you right in the middle. It's how we move smoothly from one point to another. We're going to use this one very soon.
All right, toolkit is packed. It's time for our first challenge. Before we can even describe a path, we have to know for which values of t that path even exists. This is what we call finding the domain.
So, here is our vector function for this level. It's made of 3 different pieces, right? We've got a square root, a natural log, and a fraction. And each one of those has its own set of rules about what numbers you're allowed to plug in. So how do we solve this? The trick is to treat it like 3 separate mini-problems. First up, the square root. We know you can't take the square root of a negative number, so that tells us that t has to be greater than or equal to 1. Okay, next, the natural log. Its input has to be strictly positive, so t has to be less than 5. Got it. And finally, the fraction. We all know the golden rule. You can't divide by 0, so t cannot be equal to 2. Now, here's the most important part. The vector only exists when all 3 of these conditions are true at the same time. We need to find where they all overlap.
So if you put it all together on a number line, we need t to be between 1 and 5. But we also have to punch a little hole right at t equals 2. And in interval notation, that gives us our final answer. The domain is the set from 1 to 2, not including 2, combined with the set from 2 to 5. And just like that, level 1 is complete.
Awesome job. Let's move on to level 2. Now we're going to build on that. We're not just going to find where a path exists, we're actually going to create one ourselves.
Our mission for this level is to find the vector function that draws a perfectly straight line from point P to point Q. This sounds like a perfect job for that line segment formula from our toolkit.
Okay, so we're going to start by plugging our points P and Q right into the formula. From here on out, it's just some careful algebra. We'll distribute the 1 minus t into each part of P, and we'll distribute the t into each part of Q. The very last step is just to clean it all up. Combine the 2 x parts together, combine the 2 y parts, and then the 2 z parts. This gives us that single, clean vector function we were looking for.
And there we have it, the vector function that will fly you in a straight line from P to Q as our time t goes from 0 to 1.
You can even test it out yourself. If you plug in t equals 0, you get back point P. If you plug in t equals 1, you get back point Q. Perfect. Level 2 done.
All right, you've made it. It is time for the final challenge. Now this one is less about just plugging numbers into a formula and more about being a detective, recognizing a shape from its equation. You can think of this as the final boss of our explainer today. So, what kind of path does this function trace out? We've got r of t equals 3 cosine t, 3 sine t, and just t. Let's break it down and figure it out. The key here is to investigate the components. Let's start by just ignoring the z component for a minute. Let's just look at the shadow this path makes on the flat xy plane. We've got x equals 3 cosine t and y equals 3 sine t. Now, whenever you see cosine and sine paired up like this, there's a famous trick. Square them and add them together. Because of the Pythagorean identity, cos squared plus sine squared equals 1, we get x squared plus y squared equals 9. And that is the equation for a circle with a radius of 3. So we know our point is always rotating above that circle. Okay, now let's bring z back into the picture. Since z equals t, its height is just increasing at a nice, steady rate as time goes on.
So, let's put all the clues together. The x and y parts force our point to live on the surface of a cylinder that has a radius of 3. At the exact same time, the z component is pulling that point upwards at a constant rate. So what shape do you get when you rotate and rise at the same time?
You get a beautiful circular helix. We have defeated the final boss and identified the curve. Fantastic job!
All right, let's wrap this up. Let's take a look at the new skills that you have just unlocked and think about where you can go from here.
So, seriously? In just the last few minutes, you've gained a really powerful new set of skills. You now have the mathematical language to define pretty much any path in 3D space, you have the tools to figure out where that path is valid, and you have the techniques to both build simple paths and identify more complex ones. These are absolutely foundational skills for so much of what's coming next in calculus.
And that leads us to one last thought. We now have a way to describe the position of an object at any time t. But what about its velocity? What about its acceleration? How would you find its speed at any given instant? That is a question for the next quest. And it just so happens to involve the derivative. Thanks for joining me.